Unit 9, Lesson 2, Part 1. We're going to start by diving in and looking at some of the equations that we've already examined this school year. The first is a linear equation. Then we have quadratic, and then we have higher degree equations such as cubics or quartics. Now, each of these is an example of a function. Remember, in order to be a function, every x can attach itself to at most one y value. And visually, we could also test these by making vertical lines. And the vertical line test would show that this is in fact a function, because every time I'm making a vertical line, it is touching the equation at most one time. So linear, quadratic, and higher degrees like cubics or quartics are all examples of functions. Now let's look at rational functions. Rational functions are a combination of two polynomials. In fact, the two polynomials that you're going to find the quotient of, or you're going to divide the two functions. Let's review what a polynomial function is. In a polynomial function, after all terms have been combined, so like terms have been combined, we're going to see an equation that looks like this. Every coefficient is going to be a real number. So it's going to be an integer, maybe a rational, maybe a decimal, but there's going to be no i's involved. The second part is very important. Every term will have a variable. And the exponent on that variable has to be a value that's 0 or greater, or a whole number. It can never be a negative number, and never can be an additional variable. So what it could not look like would be this. Q of x equals negative 2 to the n plus 3n to the second plus 2n to the first plus n to the 0. Why does this not constitute a polynomial equation? Because in this case, I don't have a variable that's down below, and I have, in fact, a variable that's in the exponent position. So we're examining the exponents. They have to be values that are 0 or greater, and again, they can never be variables. And additionally, when we look here at the value in front, that coefficient has to always be a real number. Okay, let's come back up here to rational functions. So rational functions are going to be two polynomials that are divided, and we get a picture that looks something like this. Sometimes it looks a little different. So sometimes we have something that may look like this. If I draw just a quick example here. So sometimes it's divided into three sections that you've seen and worked with, and it may look something like this, where we have one part that comes down, and it may look something like this. So they have different looks. But again, it does constitute a function. And how do we know that? Because every x value is assigned to at most one y. Visually, we can see that if I take the vertical line test, I only cross the function at most one time with each vertical line that's created. Now, the next two we look at, although they are functions, they do not constitute an example of being a polynomial function like the first four that I've discussed. These next two we can think of as being mathematically opposite of one another. They're inverses of one another. An exponential function that grows very fast as we go from left to right, and then we have a logarithmic function that grows very slow as we look at it from left to right. And if I drew the dotted line y equals x on both of these, and if I was able to pick this up and put it on top of this exponential function, we would see that both what the equation that we see in orange and the equation that we see in purple, in fact, would reflect directly across the line y equals x, showing that they are inverses one another. Now, just because they are not polynomials doesn't mean they're not functions. Again, every x is attaching to itself to at most one y value.